All right, in this next example, we're going to see something strange is about to happen. Suppose y equals f of x is a particular solution to the differential equation dy dx is equal to e to the negative x squared over x, such that f of 1 is equal to 7. Find f of 3. Should be easy, right? We've already done like 5 previous examples. We've got a lot of experience with this. We know what exactly we're supposed to do. Example 6. All right, our differential equation, if I'm not mistaken, is dy dx is equal to some business, e to the negative x squared over x. And then, of course, we have our initial condition of 1 comma 7, right? 1 comma 7, yeah. All right, yeah, so it looks like we don't have any y's to deal with. We just need to get rid of this dx over here. So we'd have a dy is equal to e to the negative x squared over x dx. Nice, we've separated our variables. It is time to take the antiderivative of both sides. Okay, on the left side, easy, piece of cake. It's just y, right? And then on the right-hand side, a u substitution. I don't know, I guess. Let's give it a try. So we do have like this as a composite function, it looks like. So it makes sense to try u substitution. So we go u is equal to a negative x squared, and then our du is equal to a negative 2x. That didn't help because my x is actually on the bottom here. It's not on the top. I can't actually fix that. Okay, so that didn't work. Let me cross that out. And then, I don't know, maybe if you're in BC, remember we talked about a integration by parts. Maybe it's like that. So we've got basically 1 over x times e to the negative x squared dx. So if we're going to do integration by parts, let's see, this one over here is a power function because that's x to the negative 1, and then we have our exponential. This one is closer to the u and the lipid thing, so it looks like u would be equal to, let's say, x to the negative 1. I'll write it like that, and then du would be negative x to the negative 2, or if you prefer, 1 over x squared dx. Okay, all right. And then our dv would be everything that's left over, which is e to the negative x squared dx. And then it looks like you're got to do a u substitution, but I've already tried that u substitution. It's crossed out right over here. In order to take that antiderivative, we would need a negative 2x in there, and that's not something that I can fix there, which means that that didn't work either. What that is saying is that there is no closed form antiderivative of this expression, negative x squared over x dx. I can't find an antiderivative of that. Now, I might be able to approximate it with series whenever we get to that, for those of you that are in BC. But as of right now, that's about as far as I can go as far as the general solution for this particular thing. Now, I'm going to go ahead and deal with our initial condition. So if I take a look at how this thing is formatted, what this is saying, if I read this in the other direction, is that y is equal to this antiderivative of whatever e to the negative x squared over x dx is. It's the antiderivative. So I'm going to set this up as an equation here, like this. The definite integral from, I have to use my initial condition first, which is 1, from 1 to, I guess I'll do a t here, since I already have x's in there. E to the negative x squared over x dx should be equal to, well, we just said that y is the antiderivative. So y of x evaluated from 1 to t. Okay, and then using fundamental theorem of calculus on the right-hand side, we'd have y of t minus y of 1. And our y of 1 is 7. Okay, and now I'm going to solve this equation for y of t. And I'll add the 7 over to the other side. So I have y of t equals 7. That's our initial, plus our change, 1 to t, antiderivative, or the definite integral from 1 to t of e to the negative x squared over x dx. And now we have an equation that's going to give us any particular solution that we want to, or to approximate it using a calculator. And if I'm not mistaken, it wants us to find the f of 3. So y of 3 is equal to 7 plus definite integral from 1 to 3 e to the negative x squared over x dx. And like I said, it's time for the calculator. So we'll pull up our calculator. Start a new fresh one. We need the calculator part of it. And we're starting with our initial condition, which was 7 plus definite integral from 1 to 3. And inside here, we got a little fraction-y thing. E to the negative x squared over x dx. Get inside that box. And then I wonder what it does if I just hit enter. Oh, look at that. I didn't try to approximate it, and it's like, nah, all you're going to get is an approximation because that's all I got for you. So I've got 7.109, or I can round that up to 7.110. So y of 3 is approximately equal to 7.110. And that's the best that I can hope for that particular problem, because there was no antiderivative that we could easily find at this particular juncture. All right, what do you think? Should we do another one? I think we should do another one. Let's go back to the slideshow here. Example 7, consider the differential equation dy dx is equal to x squared y. Find the particular solution that satisfies the initial condition y of 0 is equal to 5. Okay, so I'm going to give you a sneak preview of what that differential equation looks like. And we've got a slope field. Here is the little dot there. You can see our initial condition. And like from the first lesson, the previous lesson of this, we would have been able to trace off what that solution would look like. I wonder if we can do that on our calculator app. I bet we could. You know what? Let's give it a try before we even start. So that'd be y prime is equal to x squared y. I'm going to add us a graph, and then let's change this thing to a differential equation. It was x squared y, I think. Yeah, x squared y. X squared. Put the time symbol in there, and then make that y 1. And our initial condition was 0, 5. And then let's hit enter on that thing. Whoa, look at that. It looks glorious. Let's just move it around just for funsies. Okay. All right. Let's actually try to solve this. Enough playing around. All right. Example. The next one, which is 7. In our differential equation, dy dx is equal to x squared y, and we have an initial condition, which is 0, 5, and separate the variables. That's what we do, right? Let's get the x stuff over here on the right-hand side. Let's get the y stuff over on the left-hand side. So I'd have to divide the y over. I'd have dy over y. And I'd have to multiply the dx over x squared dx. We are ready to take the antiderivative. On the left side, dy over y, we've seen it 4,000 times. It's the natural log of the absolute value of y, is equal to x cubed over 3 plus c. All right, now what I'm going to suggest that we do at this point is just go ahead and solve for our initial condition right here. Let's go ahead and plug in our initial condition, 0, 5. Why did I write that down again? It's like 2 centimeters above my problem. So I plug in a 5. I'd have the natural log of the absolute value of 5, which is natural log of 5, is equal to 0 cubed over 3 is just 0. Wow, bam, we found our C value. Very, very handy. And then I can rewrite my equation. I would have the natural log of the absolute value of y is equal to x cubed over 3 plus the natural log of 5. All right, you might think that you're done, but we're not. Look at how they wrote this. Y of 0 is equal to 5. This is implying that what we need to do is that we need to solve this thing for y. So solving this thing for y, I need to exponentiate, right? So I'm going to official exponentiation color. And using our little pro tip, this thing would also get it. I'm adding with like bases, so I can use that as a multiplication. And I would have e to the natural log of the absolute value of y cancels out, leaving me with the absolute value of y is equal to e to the x cubed over 3 times, let's see, e to the natural log of 5 is going to cancel out, leaving me with just times 5. Right? And there's no plus c on this one. I already solved what that plus c is. So I might actually bring this 5 out to the front and make it look a little nicer. And then I can drop the absolute value if I put in a plus or a minus here, e to the x cubed over 3. Now I need to choose. Is it the positive one or is it the negative one? So it's like this. Is it y equals 5 e to the x cubed over 3, or is it y is equal to negative 5 e to the x cubed over 3? Well, our choice between those is completely determined by the initial condition that we have here. So I'm going to show you 2 ways to think about this. One of them is this point that we have, our initial condition, has to actually satisfy our equation, has to work in our equation. So let's just plug it in and check. So on the left-hand side, plug in 5 for y is equal to 5 e to the 0 cubed over 3 is e to the 0. E to the 0 is 1. I would have 5 is equal to 5, and it totally checks out. All right. If on the other side of the equation, we plug in our 5 is equal to a negative 5 e to the, again, it would be 0. I would have 5 is equal to negative 5, which most of the time it's just not. Which means that that is not our solution. And our solution all along should have been y is equal to positive 5 e to the x cubed over 3. So I'm curious to know if our graphing calculator will graph that for us with that initial condition. Let's see. So what I want to do is I want to add an equation. Actually, no, I don't want to add a differential equation. We're going to go to function here. And our function was 5e to the x cubed. Whoops. No. What are you doing? Here, let me actually put a fraction there. X cubed and then over 3. I think it's over 3. Yeah. And then let's hit enter on that thing. Did I... Wait a minute. Did I type that in correctly? Go to the history. 5e to the... Maybe I moved that function down. I bet that's what I did. Yeah, because that's going through the wrong point. It should have been going up right up here. All right, so there we go. If I move it up to the 5, 0, you can see that the solution works out pretty nicely. So here's something else that I think that I want to try is I want to put that negative in there and see what the heck that does. So let's go back to our history. And then put our cursor over here and put a negative sign in and then hit enter. And you can see it just flips it upside down. And obviously it's not going to go through our initial condition. So that solution is junk. We would throw it away. All right, so that's going to conclude this particular video. And I think when we come back, we've got one more, just one more. And this one is going to be a free response question from just a couple of years ago that involves all of this stuff. Put it all together in a nice, neat package.